Hello everyone. In previous lectures, we have studied complex frequency domain analysis for continuous time signals and systems. In this lecture, we will study complex frequency domain analysis for discrete time signals and systems. Include these contents for discrete time signals and for discrete time systems. Why do we need to introduce the complex frequency domain analysis for discrete time signals and systems? For this difference equation of a causal LTI system, how to obtain the zero input response and the zero state response of the LTI system. In time domain, we can use homogeneous equation to get the zero input response by convolution to get the zero state response. In frequency domain, we can only get the zero state response, and we need the input signal is absolute summable and the system is stable. Similarly, how to describe the properties of this system? In time domain, we can describe the system by impulse response, but sometimes it's difficult. In frequency domain, we can describe the system by frequency response, but we need the system should be stable. In this lecture, we will study these contents. First, we will discuss the domain representation for discrete time signals. First, we will discuss the transform of discrete time signals. Let's think about it. For this exponential signal, is there discrete time Fourier transform? No. However, multiply x of k by exponential signal, do dtft again, we can get this equation. Let z equals r times e j omega. We can get this expression. This is a geometric series of infinite lengths in the ratio 2 over z. If the condition is satisfied, we can get this result. Generalizing the idea, we can get this expression. Here, z is defined in this equation. According to IDTFT, we can derive inverse z transform. In this formula, according to the discussion, we can know x of k can be represented as a complex exponential signal. This is the definition for the z transform. X of z is a function of complex frequency, z. We use this symbol to express the z transform. Use this symbol to express the inverse z transform. Most systems in engineering applications are causal systems. To describe this system and solve difference equations with initial conditions conveniently, unilateral z transform is defined. This is a definition for unilateral Z transform. Z transform is DTFT of this signal. Hence, a necessary condition for convergence of the Z transform is absolute summability of this signal. The region of R for which this condition is satisfied is termed the region of convergence. We call it ROC. For unilateral Z transform, for region of R for which the Z transform converges is termed the region of convergence. For the unilateral Z transform, its ROC generally is the magnitude of Z greater than one real positive number. The ROC can be depicted in a complex plane. We call it Z-plane. Here, the Rx is a positive real number. The region is outside the circle with a radius of Rx. For example, determine the unilateral Z transform and its ROC for this signal. According to the definition of unilateral Z transform, we can get the result. This is a geometric series of finite lengths in the ratio Z minus 1. The sum converges provided that magnitude of Z greater than 0. The ROC can be described in this picture. Here is another example. To determine this signal's Z transform, according to the definition, we can get this expression. This is a geometric series of infinite lengths in the ratio. The sum converges provided that the ratio magnitude is less than 1 or magnitude of Z greater than 2. We can get this result. It's a ROC. We can express it in this picture. We can find the ROC is outside the circle containing the pool. For this expression, we find its pool is minus 2. Here is another example. According to the definition of unilateral Z transform, you can get this result. If this condition is satisfied, we can get the result for this summation. If this condition is satisfied, we can get this result for this summation. So, the common region for these two ROC as we can get the ROC for this signal. The ROC is outside the circle containing the pool of largest magnitude. From the discussion above, we can know the signal x of k can be represented by complex exponential signal. This is a definition for unilateral Z transform. This is a ROC. The ROC is outside of the circle containing the pool of the largest magnitude. This lecture we have studied Z-domain representation for discrete time signals. That's all for today. See you later.